Hello, I'm Shubhana Hemmati at Caltech IPAC. In this video, we'll walk through the Euclid Galaxy Clusters tutorial notebook. As you see here, the idea is to get an already published list of clusters, pick one randomly, choose a control field, and then try and see if we can find the overdensity in the area that the cluster should be, do a color magnitude diagram of it, and get all the other data, Euclid data from the archives, and investigate whether there are some differences between the cluster and control sample galaxies at the redshift of the overdensity. So the idea is basically doing a simple science example with Euclid Q1 data. Euclid Q1 data, as you might know from the previous videos, covers three deep fields: Euclid deep field south, Euclid deep field north, and Euclid deep field fornax, about 63 degrees in the sky. They are the deep fields of Euclid, but in Q1 they are to the depth of the wide survey, so they are not super deep in this first release of the data. With this notebook, we are going to exercise getting those data from the IRSA archives, getting the MER images, MER mosaics, spectra that are on the archive for this specific random galaxy cluster. I will not read through all the text here in this notebook, but the link to this notebook is under the video, and you can click and study it with more detail or change parameters. Okay, this is the link to the main paper, the Euclid Consortium 2025 paper that publishes the galaxy clusters. These galaxy clusters are the input to this notebook. They are detected with two different methods of PZ-wave and MECO. The first one is a wavelet way of detection, which finds overdensity with different smoothing wavelengths. The second one uses matched filtering, and it stands for Adaptive Matched Identifier of Clustered Objects. The second one is a bit more model dependent, so you have to assume how the galaxy models are and then look for things like that. Both of these are fine-tuned for astronomy and for finding galaxy clusters. What we'll do in this notebook is using a more general way of finding overdensity, dbScan, which is a machine learning way of finding overdensity, and we are going to see if this overdensity finder, simple one, agrees with the what this paper has already published. We will also use, as I said, Euclid Q1 MER, multiband mosaic images, and spectra, and as well as catalogs. All of these will be get from IRSA using tab queries with ADQL, etc. And it's an exercise for people who want to get more familiar with Euclid data. I am going to run these cells as we go through the notebook. I have already all the packages that are needed installed, so if you don't have them, just uncomment this cell and run it. The next one again is just importing all the libraries needed. I am going to run. Okay, successful. The next one is loading the cluster catalog from the paper that I mentioned. You can simply go in the paper and copy and paste the table, the shortened table that is in the paper, into a CSV file, but if you want, you can also use what we do here, which is reading the URL HTML and then extracting the table from it. The rest of this cell is just cleaning the table so that we can have a nice table with good columns, column names, etc. Okay, and we are just here printing the first three columns, the name of the cluster, the ID, array and deck, redshifts with the two methods of detection, etc. So here we are going to select one cluster. Here we randomly select the first one, the first cluster, which is at redshift of 0.55. You can of course change and play with this notebook with any different cluster that you'd like. Here I don't want this notebook to take so long, so I've already ran these and the data is already cached, so I'm going to just show you what we'll get with this first cluster in the list. One more thing about the clusters in this paper from the Euclid Q1 data is that they have used Viz as the selection band. So the highest redshift is about 2. And in future releases like DR1 clusters, this will be pushed to higher redshifts by including the near bands also in the detection. So, okay. So here's the cluster field. We have put a criteria of when you look for the center, finding only 4 mere science images, and these 4 stand for V's as well as NISP, YJ, and H. Sometimes if the center of the cluster is close to the edge of the tile, then you'll find more than 4 mere tiles, and that would just make downloading longer and make plotting a bit more difficult. So that's why we have this criteria. It's not needed, it just makes the notebook a bit cleaner. And how we define a control field is by randomly moving away from the cluster center and choosing an area with a similar size in the 4 bands and calling it a control field. The probability of it having a cluster is of course lower compared to knowing where the cluster is. So we call that a control field. You can run it different times, get of course different control fields. But again, here we set a random seed and you can change that random seed to get a different cluster. Okay, so here again, the control field, the array and deck, and it found exactly 4 images in this coordinate. If again it's close to a mere tile edge, then it will run again. So there is, I think, a criteria of trying 100 times to find a good match. So you can just leave this running and it will eventually find you a good coordinate for the control field. In section 3, we get to downloading data and caching. We go for a 12 arc minute size for the image cutout, and we get them from an S3 bucket on AWS where the Euclid data are hosted, and we download the files the first time that this coordinate is given to this notebook, so that if we want to run many times with different parameters of overdensity detection, we don't have to wait for this download for a long time. So again, you can read all the details of these functions if you're interested. And here, because this is already downloaded and cached, you can see that 4 bands for the cluster and 4 bands for the control field are already cached and downloaded. Here showing the size slightly smaller for the cluster field, but and that is just that just depends on where we hit the edge of the mere tile. If you are the first time running this might take, depending on your internet speed, between 7 to 30 minutes to download. Next, we just have some functions that visualizes each of these bands, as well as an RGB image made from combination of V's plus J plus H. So there are functions of how to change the stretch, how to do the same color bar for all of them, how to make sure you're not saturated by a very bright star, and how to downsample a bit before plotting, so that it doesn't take so long to give you a visualization of these 2 fields. Okay, so here we have on top the cluster field, on the bottom the control field. You see the V's, Y, J, and H band, as well as the RGB image at the end, and the size 12 arc minute by 12 arc minute that we selected. Next is to try to get the galaxies that fall in these fields, in these coordinates, and we need their photometric redshift, so that we can select only the ones that fall in the redshift bin of this cluster, which is 0.55 with some width. So here we run these functions that query the galaxies for the cluster field first, and then it will get to the control field. So it found 517 galaxies in the cluster field at redshift of 0.55 plus and minus 0.12. You can of course play with this number and change it depending on how big you want the width of the redshift bin to be. 0.12 seems reasonable given that these are photometric redshifts and the uncertainty isn't that small. If you have spec-Z, then you can of course make it smaller and be more critical of what can be counted as a member of an overdensity. Already from the number of galaxies in this bin, you can see that there are way less number of sources found in the same area for the control field compared to the cluster. So the ratio is about 2.65 and the overdensity is 1.65. So that's the first sign of yes, there is a cluster there that you can see from the overdensity. Then we use dbScan, as I mentioned in the beginning of this video, which stands for density-based spatial clustering of applications with noise. It's an unsupervised machine learning general technique of finding overdensity. It has two different parameters. One is called epsilon, which is the radius to which something can be counted as a neighbor, and then it also has mean samples here, which is basically the minimum number to be considered a density. These two numbers you can play with to find something that is reasonable, and it of course depends on the your pixel scale and your definition of galaxy cluster, etc. So here I am running this dbScan with an epsilon of 700 and a minimum sample of 25. I am giving it the galaxy data frame, which is all the galaxies that we queried from the Merkle log. And the WCS is used to convert the array and deck to physical X and Y, and the reason is that this epsilon then knows about pixel scale rather than array and deck. We are doing this on an RGB image, so compared to what the paper does, which is only V's, we are using RGB, but it can be changed to anything. And then field name here just is either cluster or control field, so that it knows which one we are running. Okay, so running that, and then this is basically saying with these epsilon and minimum samples, we find one cluster in the cluster field and 0 clusters in the control field as expected. So if you play with those numbers, if you make the mean sample small, if you make it very small, then you start to find things on the control field as well. And if you change epsilon, then that mostly changes the size of the clusters that are found. For example, if you change this 700 to something like 500, then you'll find 2 clusters in the cluster field that are very close to each other, basically two neighboring clusters. So you can play with those numbers until you're happy with it. So how dbScan works is that it, based on the epsilon and minimum sample, it defines a point as a core point. Everything next to it will be, I think, an edge point or something like that, and everything that doesn't meet the criteria will be a noise point. So here, when it says 195 noise points, it means that all these 195 galaxies that were in the redshift range of our cluster at 0.55 plus minus 0.12, none of them were neighbors and met the criteria. And here there were 190 things that didn't meet the criteria. Okay, so if we plot these on the RGB images, here's what we get. So on the cluster field, these are the things that are identified as members, and here, as you see, nothing is selected in the control field. If we go ahead and do a color magnitude of the galaxies that we identified as members of the cluster and the control field, you can see that so we go with Y and H, the color magnitude diagram. I'm just running these to get to the main plot, which is this one. Okay, so we have a Y minus H color and H magnitude, and the blue contours show the field, the red contours show the cluster members, and as expected, we see the very tight red sequence in the cluster field compared to the more spread and the blue cloud that you see in the field. So it's not that the cluster, of course, doesn't have these bluer galaxies, it's just that the concentration of the red sequence galaxies is larger. So this is just another way of confirmation. It's not a big discovery, as all astronomers probably expected to see something like this, but we are just playing with the data, showing how the magnitudes and colors can be queried for different samples from IRSA. Next is querying the spectra from for these two different samples, with having in mind that this is Q1 data and the quality of the spectra is not super great, and also having in mind that we are using photo Z's, and when we stack the spectra with photo Z centering, there is a good chance of washing away any signature that exists. The idea behind it is to have this notebook run on better spectra, DR1 spectra, and with a spec Z, so have everything in place to try to see features. For example, whether we do see more prominent emission line in control sample compared to the cluster, whether we see some specific line ratios in the cluster field that we don't see in the control sample, etc. So it is so that is the main idea behind this. I don't know if I ran this, sorry. So running this again, if it's the first time you're running it, it will probably take slightly longer. I have here set n equal to 10, which only gets the first 10 spectra from each of these fields, and the reason again is because the quality of the spectra is not super great and we don't want to wait forever. If you want to query all the spectra, you can just increase this n to the number of sources that exist in each of these fields. Okay, here we have a list of prominent emission lines to be plotted, overplotted on our spectra, and we do some basic processing, for example, not plotting the bad quality parts of the spectrum. There is a mask that we use, and here we build a stack, again, as I said, using photo Z, so there is some chance of washing away things, and finally getting to the spectra. So as you see, I try to prepare you for seeing something like this. We don't see any prominent emission line. We see basically noise being stacked on top of each other, and hopefully with better spectra and with the spec Z, we'll start to see at least better stacks. The final section of the notebook is to query NED in these same coordinates and see if we find members of this cluster with NED already. And here it says that in the cluster field, and of course the idea is trying to use another archive on IRSA, which is NED, and match it to Euclid. So it also showcases two archive usage in one notebook, and here it found 207 total NED objects in this coordinate of the cluster field, 45 had redshifts, and 35 of them were in the redshift range that we are interested in. And here are the objects. We repeat the same thing for the control field. So 855 total net objects in that coordinate in that box. 12 had redshifts, and only one was in the redshift range that we are interested in. So just overlaying the ones that net found compared to the ones that we confirmed with with DB-scan previously. And you can see that some of the galaxies that net suggests are in this redshift were already missed by our DB-scan as candidates. So these might be interesting objects to follow up and see what has happened here. Okay, and last but not least is whether to see there is any agreement between the net redshift and the Euclid redshift, and this is really not great. Of course, the width is small, but both probably photometric redshifts, and the scatter is large. That's all we have in this notebook, but you can play with it with, as I said, with different clusters. This was just shown for one cluster here. You can change the control field, you can play with DB-scan parameters, and do any other kind of querying of their spectra, their photometry, etc. I hope this was useful.